Hello again. We're going to now talk about bigger sugars that arise from glyceraldehyde ultimately. To remind you about its structure from the previous video, here is the Fisher projection of D-glyceraldehyde. To highlight the stereochemistry, I want to remind you that when the hydroxyl of the penultimate carbon is pointing to the right, this is considered a D sugar. Okay, if the hydroxyl of the penultimate carbon points to the left, then this is considered an L sugar, right? But it is the case in nature that the predominant version of sugars is the D version. So we're going to continue talking throughout the rest of this lecture about D sugars. But remember that for any sugar that we talk about here, if you want to refer to the L sugar, the enantiomer, you will have to draw the entire mirror image of that D sugar. All right, now in terms of deriving the rest of the aldose sugar, so now we're looking at the aldotetrose sugars, meaning sugars that contain the aldehyde moiety, but in total you have 4 carbons. So the way that this works out, if we stick to these sugars, is that the bottom portion of the new derived sugars is going to be a copy and paste situation from the bottom portion of glyceraldehyde. Basically, you stop 1 carbon short of reaching the carbonyl, and you just copy that down. And also the aldehyde, right, since we're going to stick to the aldose for now, the aldehyde at position 1 will also be kind of copy and paste. So aldehyde in position 1, position 4 will still have the CH2OH, and then at position 3 in the new sugars will have HOH with the OH pointing to the right. So this last portion that I'm highlighting in red, it's literally copy and paste from the bottom portion of glyceraldehyde. And basically all that's going to change is that we're going to add another water equivalent, another HOH component to the horizontal, which kind of brings me to one key point. You may have heard of sugars as being referred to as carbohydrates, and it's not a mistake, because really what you're doing is you're taking a carbon chain and you're adding a water equivalent, HOH, right? So that's what we're going to do here. We're going to continue carbohydrating this molecule. So on the one hand, you can have the OH pointing to the left side, but this is not the penultimate carbon, so don't be confused. This is the carbon that follows right after the carbonyl. So we could have the hydroxyl pointing to the left, but we could also have it pointing to the right. And what this means is that you are actually looking at 2 different sugar molecules. Now, it doesn't change the fact that the penultimate carbon, and now this time around the penultimate carbon is carbon 3, right? Because you have 4 carbons in total. The penultimate is 1 less than the full count, right? So position 3. It doesn't change the fact that this penultimate hydroxyl is pointing to the right. So both of these 2 sugars, which are different from each other, but these 2 sugars are D sugars, okay? And they are deriving from D-glyceraldehyde. All right, now the one that has the other hydroxide, the second hydroxyl to the left, this is known as 3-ose. And the one that has the hydroxyl pointing to the right is known as erythrose. And I know the names are a little bit funky, so if you've taken this class with me, then you know that I'm going to provide you with these names and the Fisher projections, because there's no need to memorize all these sugars. Probably the only ones that you should maybe memorize are glucose, fructose, and maybe galactose. But the rest of them, yeah, no, they don't appear. They don't appear as much in nature. Definitely not like glucose and fructose. So there is no need to memorize them. But anyway, the way we're deriving them, as you can see, is pretty much just copying and pasting the bottom portion of a smaller sugar and then just adding HOH to the new incoming carbon content. So you might find it not surprising that we could basically follow that technique once again, take 3-ose as well as erythrose, and simply apply the same logic again. Now this time the carbon that appears, basically falls short of the carbonyl carbon will be position 2. And that's going to be true for pretty much all the sugars we're going to look at. But what this means is that in order to derive the higher sugar, we're going to copy the entire carbon chain of 3Os up, from carbon 4 all the way up to carbon 2. Okay, and that's literally what I'm doing right here. I'm copying carbons 4, 3, and 2 of 3Os. And I'm doing it twice because just like we derive 3Os and erythros from glyceraldehyde, for the incoming carbon, the new carbon that's about to show up in here, we will have the option of the hydroxyl pointing one way or pointing the other. So the same thing is going to happen with erythros. We simply copy carbons 4 up to carbon 2 exactly as they are over here. And here's where the fun begins. So the new carbon, so the new horizontal line that we're going to apply right here will give us the new sugars. Oh, and by the way, all of these sugars have the penultimate hydroxyl pointing to the right. So all of them are automatically D sugars. And yet again, they're all derived from D-glyceraldehyde, right? So that's the denomination. So in the case of the rest of the molecules, right, we'll have this new horizontal line where we're going to have HOH. But after that, or before that, depending how you want to see it, you will have to have that aldehyde component at the very front of the molecule, position 1. So that this will be true for all of them. So really the only thing you have to do is for carbon 2, you will have to have in one instance hydroxyl to the left. This will be true for the 3Os derivative as well as the erythros derivative. And on the other instance, you will have to have that OH pointing towards the right side. Okay, and then if you look carefully, you should realize that all four of these variants are in fact different molecules. None of them has a repeating pattern. And you got to remember, these are chiral centers. So the fact that they are different, even if one of them is different from the other, that makes the whole molecule unique. If you want to be technical, it's a diastereomer of the one that you may be comparing it to. All right, but these things will have their own names. So the one where we have from top to bottom, 2 to the left and 1 to the right. And when I say that, I'm talking about the hydroxyls. 2 hydroxyls to the left, 1 hydroxyl to the right. This is known as lexose. If you have this back and forth, one right, one left, one right, you got D-xylose. If you got one left, one right, so 1 to the left, 2 to the right, you got arabinose. And if you have all three of them pointing to the right, then you got yourself ribose, which is also one of the common sugars encountered in nucleic acids. So that might actually be one to perhaps remember. All right, so what you're seeing right here is that we started with glyceraldehyde, only one sugar, one trialdose. From there, we derived 2 tetraaldose sugars, 3Os and erythros. And then this keeps on multiplying, right? So it's basically 2 to the n, depending on how many carbons you have in between. So we go from 2 sugars, now deriving 4. So you probably already guessed it. When we go from the aldopentose sugars to the hexapentose sugars, we'll have a total of 8. So we're going to basically do that right now. Derive those 8 6-carbon chain sugars. And we're going to start first with lexose and xylose. I would have loved to put all of them in one slide, but it was just it was just too hectic, and yeah, so I just decided to break it into half. So I'm only working at the moment with lexose and xylose, the 2 sugars that derive from 3Os, and then right after that we'll deal with the erythros derivatives. Okay, so here it is, lexose and xylose. Just like in the previous scenario, we're going to take carbons, in this case now carbons 5 through 2, and we're just going to copy and paste that to derive the 6-carbon sugars. Okay, so we literally take lexose from carbons 5 to 2, and we just copy that exactly as is, no difference. And we do exactly the same thing with xylose. We copy the structure from carbons 5 to 2 exactly as is, 2 of them, of course, but other than that, the structural features are identical. Okay, then what we do is we acknowledge that this top carbon is going to be where the new horizontal line is going to appear. So we go one step further and introduce the aldehyde that has to be there for this to remain an aldose sugar. And then we did exactly what we did in the previous 2 situations. We'll place hydroxyl to the left, and once for lexose, the lexose derivative, and then once for the xylose derivative. And then we'll place the hydroxyl to the right, for one of the lysose derivatives and one of the xylose derivatives. All right, so here's same dealio. The penultimate hydroxyl is automatically pointing to the right, so by default all of these sugars are these sugars, but they are all different from each other. The first one, where we have the 3 hydroxyls to the left, one to the right, is the talose. When we have 1 to the right, 2 to the left, 1 to the right, we have galactose, D-galactose. When we have 1 to the left, 1 to the right, 1 to the left, 1 to the right, basically full-on intercalation, we are dealing with idose. And by the time we get to this last one, where we have 2 to the right, 1 to the left, 1 to the right, we are dealing with D-gulose. Which, yeah, they all have kind of funny sounding names, but it has to do with the suffix of all these molecules, right? I told you, I think in the previous video, if I'm not mistaken, that the ose ending is not a coincidence. In fact, if you scan carefully all these sugars we have here, they all end with ose. That's not a coincidence. It's part of the nomenclature. Ose tells the reader that your molecule is actually a sugar. So that's why they all end with ose: idose, gulose, galactose, talose, lysose, xylose, etc., etc. All right, so we have 1, 2, 3, 4, 5, 6 carbons. This is only half of them. Now we're going to look at the other half. All right, so arabinose and ribose, the 5 carbon sugars. We do exactly the same thing as what we did just a second ago. We copy carbons 5 to 2 exactly as they are, and we have 2 sets of them. So we have, carbons 5 and 2 just identical, right? Just copy and paste. Same thing for ribose. Carbons 5 through 2, you copy exactly as they are, no difference. And because the penultimate hydroxyl is pointed to the right, automatically all of the sugars will end up being D sugars. So we acknowledge that this position is going to be the new aldehyde position. And not only that, in one instance, we'll have the hydroxyl pointing to the left at the second position. That will also be true for the ribose derivative. And on the other instance, we'll have the second carbon with this hydroxyl pointing to the right. So this will give us all 4 additional 6-member carbon sugar chains, the aldohexose sugars. Okay, so the one where we have 2 to the left, 2 to the right is known as mannose. The one where we have 1 to the right, 1 to the left, 2 to the right is known as glucose. This is the famous molecule, so this one you might want to remember that pattern: right, left, right, right. And then the next one where we have 1 to the left and 3 to the right is known as aldose. And the one where all 4 of them are pointing to the right is known as allose. And with that, we basically have covered the family of aldose sugars from a 3-carbon chain all the way to a 6-carbon chain. Altogether, we are basically talking about a total of 13 different sugars, right? Which, it's a little too much to memorize, especially the patterns. But glucose, fructose, that I'm going to show you momentarily, and ribose may be important. Galactose is one that you will encounter once a little bit later, so maybe that one is one to remember. But glucose for sure, fructose for sure, and then ribose. Okay, so this basically concludes the aldose sugar. So in the next video, I'm going to show you, the same thing happening with the ketose sugars. So I'll catch you then. Bye bye.